This program was brought to you by Coller Institute of Venture at Tel Aviv University.
So first, contents of my presentation. I will make some kind of overview on the need of wave energy and the need to extract wave energy resource, then some possible applications of wave energy, not only power production. Then the structure, very briefly, the structure of a wave energy converter. My colleague mentioned already a few things about this topic, so I will just mention a few things on the main components, what kind of technology we are talking about. Then I will underline some of the current main challenges we need to face in order to shorten the path to commercialization. And finally, I will show a bit some aspects of the most promising technologies. So, why wave energy? To answer this question, we need to answer a few other questions. And the first one is to understand how many we are. Nowadays, we are more or less 6.7 billions. The population will increase till around 9.2 billions in 35 years. And of course, this will put some pressure on the demand of energy. So the power production will increase from 90 gigabarrels of oil equivalent per year to about 110, 105 in 35 years. This shows already a very, very huge problem we will face, because the rate of increase in power demand or in power production is not exactly the same as the increase of population. So at around 8 billion people in the world, the resources will start decline. And this is exactly what we can see here about 8 billion when the population reaches the level of 8 billion people. So this is a very huge, of course, from now on, from this black line on is a foresight exercise. Other scenarios were established, but more or less in the scientific community, everybody agrees with this, or at least think that this is the most realistic scenario. What is the consequence of this scenario? Is the increase of pollution. So this green line shows basically the CO2 emissions associated to fossil fuel consumption, not other gases, just CO2 emissions. And we will think that the increase will be from 9 billion tons of carbon per year to 23 billion tons of carbon per year. And of course, the consequence, this is the scenario, I don't remember pretty well, but I believe that this is the scenario to keep the warming, the global warming, below 2 degrees. So of course, this is a problem, and this is a problem that we can easily understand why will happen, because if you decompose the world energy production into the different sources, we'll see that the main sources is and will be coal, oil, and natural gas, which have a huge impact on CO2 emissions. The contribution for the mix of energy from renewable sources is quite limited, and we believe that this is the space for wave energy. So wave energy, if you look into the map all around the world, these numbers in the coastlines basically translate the wave energy levels, and means that each meter of wave frontage transports this level between more or less 0 and about 100 kilowatts per meter, which, if we integrate this potential all around the world, we'll end up with a potential wave electricity generation of about 12–15% of the world electricity consumption. This value takes into account some non-technological barriers, some constraints related to, for instance, fisheries and fisheries industry and maritime routes. All these constraints were considered in this estimate. Of course, I'm not saying that wave energy will be the solution for the environmental problems the world is facing. I'm just saying that is probably one contributor to the solution, and I'm pretty sure that wave energy will be a quite important part of the energy production mix. But not only power production, because if we look into another world problem, which basically is water desalination, and if we superpose the addressable market of these different areas all around the world, and the addressable market basically underlines the need of water desalinated, we'll end up with a conclusion that we can easily understand that in many areas where we have water issues, the level of wave energy is pretty high too. So this means, I mean, the conclusion is pretty basic. This means that the technology for wave energy harvesting can be used to desalinate water. And basically those are the two main applications for wave energy technologies. There's another one I skip because it's a niche market. It's basically small application for recharge ROVs batteries and buoys for signalization, routes and so on. But this is very niche market. So the main part is, I'm convinced, power production and water desalination. So now I will show a bit. I will talk very briefly about the structure of wave energy. As my colleague mentioned before, there's a huge round of different concepts. No convergence was achieved, but we can summarize the concept in a very simple way. Basically, a wave energy converter is composed by a capture. A capture is the part of the component of the device that is excited by the waves, and is excited and then it moves with the waves and moves against some kind of reference point, and this reference point maybe is the reactor, which may be another body or the sea bottom. Then in the middle, to convert this mechanical energy from the motion into electricity, we have a power takeoff system, and basically that's it. Then we have the umbilical to transport the electrical energy into the substation and then into the grid, to feed the electrical grid. And ultimately we have a sea-keeping system or mooring system to keep the device in place. So the device is basically the so-called mass spring damper system. Is a pretty simple equipment. Now the question is, if the system is so simple, why we didn't succeed yet to have some commercial device in the farms of wave energy converters in the sea? This is the main question, and the answer, I believe, is represented in this slide. The question here is not exactly the work principle and how we can extract energy from waves. The main question is the cost efficiency of the concept. So we believe that the problem is to reduce this levelized cost of energy and make the concepts more cost efficient. And to do so, and basically the problem of the high levelized cost of energy is underlined in this graph, where we can compare different sources of power production, electricity production, and we'll see that, of course, this is an estimate because there's a gap of a lack of data to produce these estimates. But basically, these estimates indicate that the wave technologies, the LCOE of wave technology, may reach the level of $400 US dollars for megawatt hour, which is huge compared to all the other sources from nuclear, coal, gas, and so on. So to address properly these aspects, and in order to reduce the levelized cost of energy, there's a lot of different areas we need to look at, but three are the most important factors. The first one is survivability issues. This means new materials cheaper than steel to undertake the extreme conditions sometimes the devices are facing in the water, is a very, very important aspect and makes a bridge with material science, for instance. So this is one point. The other one is control strategies. Of course, everybody knows, looking into the ocean, that the waves are pretty irregular, and the main issue behind the control strategy is to adjust for each different sea conditions, adjust the characteristics of the power takeoff to optimize the power capture. So this is another very active research topic nowadays. The thing is that the control strategy, of course, the focus is reduce the levelized cost of energy, not by reducing the costs, but by increasing the power capture. And the last vector, also very important, already underlined by my colleague, is the reliability of components. So the reliability has a huge impact in maintenance costs. So the thing is that if we have a much more reliable system, we will reduce cost on maintenance, and then this will end up with a reduction on the levelized cost of energy. So these three areas, I think, are the most important areas, and basically those were my criterion to select the next slide, which basically are the most promising technologies. So I select three technologies. This is one of the first. I select based on this concept. Developers that are looking into control, survivability, and reliability. The first one is a Wedge Concept. Wedge is a company, a Spanish company. Spanish/US company, because they have a branch in the US already. Basically, it's a forced reacting device principle, which basically has a floater and a submerged mass. The submerged mass is the reactor, and the waves induce some relative motion between the two parts. In the middle, there's a power takeoff system, is a linear generator. I'll skip the details, but basically a linear generator is a generator like a common generator, but instead of transforming the mechanical energy of a rotation, it transforms into electricity. It transforms the linear motion or the translation motion. So basically we have a few pictures. One is basically just the schematic power takeoff representation. The other is the PTO, this linear generator itself, the lab tests they did during a long program test. I don't know, more than 2 years. They test this component in the lab in Madrid. And here in the top we see a picture of the real prototype in real sea conditions. So this was built and deployed 1 year and a half ago in Spain, in the Canary Islands. So now just to look a bit at the approach, which I believe that is a very wise approach. The company is following this LCOE reduction. They first start from this first generation device, which has a cost, or had a cost of 45 cents of euro per kilowatt hour. This was the LCOE. Then they look into new materials, new advanced control, new operation and maintenance issues, reliability, all these type of different things that may affect the LCOE, to end up with a new generation, with a new concept, a new generation, with an LCOE of about 28 cents per kilowatt hour. Is still high. This LCOE is still high, but they may be already competitive in some niche markets where the power production is very expensive, like in Iceland, is a problem in the US, in Hawaii, for instance, and even in Europe. The Canary Islands is a very good example, because the cost of energy, it oscillates between 25 and 30 cents of euro per kilowatt hour, which means that with this device, in a very early stage of development, the company may reach some kind of competitiveness. Okay, so the second device is basically the same approach. Is a pretty different device from the work principle point of view. Is basically a duct-shaped buoy with a U inside, and the U is partially full of water, and the water is sloshing inside this U, and putting a column of air going forth and back to an air turbine, and then the turbine is connected to an electrical generator, and which basically produces electricity from the rotational motion. This concept, the approach for the development was pretty similar, because they also look into the survivability issues. making the structure partially in concrete, which is much cheaper than steel, and producing the device completely closed, which give is also a benefit from the survivability point of view. No relative motion between different parts. This is also an improve. From the efficient point of view, they extend the degrees of freedom used to extract energy, not anymore only the heave motion, but also roll and sway. And basically this is the approach. The thing is that this concept is in a very early stage of development, much earlier than the one I mentioned before. This concept is basically, the concept was proved in wave tank trials in France, but they are thinking probably in 2-3 years they will be ready to install a prototype in real sea conditions. So the last concept, I'll skip the details because this is the topic of the next presentation of Patrick. He's around, I believe. Yeah. So this is also a very, very promising concept, which addresses the three main vectors I mentioned before: survivability, because it's very compact, high efficiency, the control, and reliability, less components. But again, is very promising, and so I think, Patrick, jump into the stage and you can present the next.
This program was brought to you by Coller Institute of Venture at Tel Aviv University.